Hello, and welcome to a sort of extension video of one of our previous white paper presentation videos. That one was on EMI filtering, and one of the common components in an EMI filter is a common mode choke or common mode coil. So I made this separate video to dig deeper into that specific component to help anyone maybe expand their background on this particular magnetic, or just to provide some additional insight if anyone's coming over from that video. So this is basically what we're going to be talking about in this presentation. It is a passive electronic, which basically means that it doesn't require any power to operate other than what's going through it. It acts on the power that's going through it. It acts as a noise filter, which is why I had mentioned its tie-in with the other white paper that we had made on noise filtering. And then we'll talk a little bit about the construction, some of the shapes, some of the materials, some of the winding options. So first off, just hitting on the fact that it's a passive electronic, it's incapable of controlling current by means of another electrical signal. As I had mentioned, it just means it only acts on the signal going through it. There's no control signal, there's no on state or off state or anything like that you might find with an active electronic. A common mode choke or common mode coil is a type of inductor that uses magnetism to store and release electrical charge through current. And the currents going through it generate an electric field, as all currents do in a coil. This causes impedance at high frequencies because this electric field opposes the change of electric fields, opposes the change of currents. And so at higher frequencies, you're having that change kind of battling with the frequency wanting to change at a very high rate, which leads to a very high impedance. So now we're going to jump over into defining noise. And electronic noise is basically anything other than your signal that you're trying to send through your circuit. Any unwanted noise, any interference, that's all considered noise. And there are a lot of different causes: electronic switching, interference of another signal. And those are kind of covered in more depth in the other video I had mentioned at the top of this. It's a white paper presentation on electromagnetic interference and filtering. So you can check that out if you want to know more about some of the causes of electronic noise. But there's two different types of noise, and it depends on how it gets into your circuit. If it gets in through physical wiring or physical contact or a shared ground plane, anything where it's conducted, we call that conducted noise. And then on the other side of that, the rest of the noise is encapsulated in what we call radiated noise. And that's anything that is radiated out into the air, travels in a non-physically connected way to your circuit from a noise source, and then is attenuated into your circuit through a coil or a wire or anything acting as an antenna to kind of receive that radiated signal in as noise to disrupt your signal. So we're going to jump into the common mode coils or common mode chokes, abbreviated as CMC. For the future of this presentation, we're just going to continue to use that acronym CMC. We'll talk a little bit about their performance and protection. So a well-designed filter can ensure clean power and clean signal getting into your system or your circuit or your application, prototype, anything you're working on. So this clean power can help reduce wear on electronic motors and anything that physically switches, any switching equipment. Anything very sensitive can be damaged, destroyed, or even stop functioning altogether with too much or an overabundance of noise. So having clean power signal is very important, whether you have something relatively robust and insensitive like a motor, all the way down to very delicate equipment such as sensors or encoders, anything like that, that is going to be looking at very small changes in a signal to try to operate effectively. In addition to protecting the equipment, it helps your equipment operate at a higher efficiency and a higher reliability. There's less wasted power, and you have fewer interrupts of operation due to failures from noise. So there's a couple of different kinds of noise. We're obviously going to be focusing on one. You could probably guess from just looking at this slide which one we're going to be focusing on with the common mode choke. But there's two different kinds of noise in any circuit. One is the common mode noise, which, in case you hadn't guessed, that's going to be the one we're focusing on. And noise in a common mode noise is common or the same in both the line and the neutral, or the line and the return, and then comes back through the ground. So as you can see here, these gray arrows both going in the same direction on the line here and the return, and then going in the opposite direction on the ground. So they're actually coming through together on the line and neutral and parallel, and then they're circling through and returning through the ground. This is different from differential mode noise, because differential mode noise goes through your circuit much like a power signal would. It just goes through the line and comes back through the return. So these different types of noises can be attenuated and have to be treated and filtered differently. So we're going to jump into a common mode choke, CMC construction. And since we're facing common mode noise, we have the gray arrow here. That's the common mode noise, if you remember from the last slide, going in the same direction through this coil. So an interesting trick we could do is if we wind this coil in opposite directions on both sides. See, this one is coming in this way and going around. This one is going in the opposite orientation. If you remember your right-hand rule from physics or electronics, or whatever you were taking to learn about electromagnetic fields, you can see that these currents will oppose each other, and that effectively cancels out any current seen by this gray donut. This is going to be the core material of the common mode choke. So basically, in order to achieve this desirable condition of zero current seen by the core, we have to make sure that it's the same number of windings on both sides and they are in opposite directions. If they're in the same direction, you could cause your core to saturate and it will effectively not function. So moving on to some of the information about the magnetic core, it's going to be a toroid shape or another closed loop shape. So sometimes they come in rectangles or E-cores, etc. But it's going to be some kind of closed loop shape, whether that's rounded edges, squared edges, etc. The other important marker for a common mode choke core is that it's going to be very high permeability. Typically in core materials, you have a trade-off of permeability and what's called saturation. So saturation is effectively when current increases going through a choke, it will have an adverse effect on the inductance of that same choke. So as current increases, the inductance drops. And inductance is directly tied to impedance, which is what helps you attenuate a noise signal. So as current's going up, your attenuation and effectiveness to filter out noise is actually dropping. So that's obviously not what we want. But since we're not dealing with any current because it's canceling each other out from the line and the return here, we can go as high a permeability as we can and we don't have to worry about saturation, which is great news for a common mode choke or anyone trying to filter common mode noise. So that's typically what we'll see. We'll see very high permeability because there's no trade-off for the saturation being lowered, saturation current being lowered. here are a couple of example core materials. Um, some of the considerations when looking at different core materials, you obviously have to consider the copper loss. So that's going to be from your permeability. Basically, it's indirectly tied to that, because the higher your permeability, the fewer turns, which is the windings of copper wire around the core you're going to need to achieve a certain inductance. So if you have very high permeability, you need very low turns, so you need less copper wire, so your copper loss is going to be lower. Then the other consideration is core loss, which is basically how effective that particular core is at using the energy from the electromagnetic field generated by the inductor at impeding the noise and not turning that into thermal energy or thermal waste. So you can kind of see at the end column here is an estimated total loss in watts. You have size considerations in the second to last column. Obviously, anything in electronics is going to be driven somewhat by size. You can't just have an infinitely large core or common mode choke to get massive amounts of attenuation everywhere you go. You're going to be constricted by size. Permeability here is what I was talking about earlier with the tie-in to some of the losses. And as you can see, this nanocrystal has by far and away the highest permeability. And we don't have it on this chart because it's not important to a common mode choke, but it's harder to use nanocrystal in other applications because as the permeability goes up, the saturation current tends to go down. It's not a direct correlation, but it is a relationship between those two. And then the final consideration here, which is the first in the column, is cost. So there is a high cost to pay for this high permeability. So you have to factor that into your application, your specific circuit and design, whether this higher upfront cost is worth lower core loss in the future, whether it's worth a smaller space so that you can make your product smaller, whether it's worth that increase in efficiency to have a very clean signal coming into your circuit. These are all the things you would have to consider when deciding on your core material. So another thing to consider when selecting or designing a common mode choke is winding options. There's two basically predominant wire types. One is flat wire and one is the standard or round wire option. Flat wire can also be called rectangular wire. One of the drawbacks for flat wire is it's a little more expensive, but you can get a higher turn density, as you can kind of see here. These, especially on like an E or C core, you have a flat surface that these all can just stack up on really nicely. Whereas the round wire, you don't get that same nice stacking even on an E core. Obviously, this is on a toroid, so it's not going to be exactly one-to-one in looking at it. But as you can imagine, you're going to get a very high efficiency of winding / stacking rectangular wire versus round wire. It's the same reason boxes for shipping are some variation of a rectangular prism, whereas you're not going to see very many tubes or round boxes to ship. They don't stack nicely, so you don't get as high of a storage efficiency, space efficiency with that copper. The other thing for flat wire is it's got low DCR versus thickness, because you can kind of send it in multiple different directions. You can have wider wire, you can have thicker wire, you can have, well, pretty much those two, because the length is going to be predetermined by the number of windings. So you can either make these a little bit taller here, a little bit thicker, or you can make it stand out from the core a little bit more. You can have your wire there. Whereas round wire, obviously by the nature of being round, it's already got a fixed ratio of kind of width and height, because it's really just the radius or diameter. The final benefit of flat wire or rectangular wire is that it has good high frequency performance. If you know about the skin effect, then you can already kind of guess why this is better. But the higher the frequency, the closer to the surface the wire is effectively used by the signal going through it. So I guess to kind of say that a slightly different way, as frequency increases, you use less and less depth of the wire. And so the surface area becomes what drives high frequency performance. With rectangular wire, you have more surface area per copper, whereas the round wire, you have less surface area per copper. So at high frequency, using the same amount of copper, the same DCR, you're going to get better performance from a rectangular wire or flat wire than you are from a standard wire. The advantages of standard wire, though, are that you have more affordable options since it's so common to use standard or round wire. The volume versus price situation is going to be in the consumer's favor. And then it's a uniform shape, which sometimes makes multi-layer windings a little bit easier. And it's you don't need any special equipment to wind round wire versus flat wire. So that's another way it's more affordable. The other options in winding common mode chokes are bi or tri-filar, which basically means you have 2 or 3 or more strands basically functioning as one strand. If you think about like multi-line or Litz wire or something like that, those are similar concepts, though Litz has a particular way that it's woven together to reduce certain interference from those lines woven together, but that's a separate story. It's just those multiple strands of copper acting together as functionally one wire. You can also do that on either of these cores. So if you have any questions about common mode chokes, any magnetics, any of our videos or presentations, feel free to reach out to any of our global locations or just reach out to ITG with any of your projects, and we'll help. We make a lot of custom magnetics, custom components, so we're happy to answer you through any of these means. Thank you.